Good morning and welcome to Unit 8. So, Unit 8 is all about something called sampling distributions, and I do want to take just a moment to remind you what a sample is before we dive into this. So, let's say that you were wondering about how people in Bowling Green felt about the fast food options that were available to them, and so you want to give them a survey, right? Well, it wouldn't be feasible for you to go to everyone in Bowling Green, so the entire city of Bowling Green would be your population. Let's say you decide you are going to randomly give the survey to 300 people. Those 300 people would be your sample. So then a sampling distribution would represent all possible samples of size 300. So in the city of Bowling Green, with as many people as it has, there are literally millions, if not billions, of different samples of size 300 you could take, because changing even one person out of the 300 would be considered a new sample. So let's look at this on a smaller scale, just to get an idea of what's happening. So let's say that I had a class of 4 people, and those 4 people took a test, and their scores are shown right here, 60, 70, 80, 90. So because those scores represent every person in the class, that would be my population distribution, and that's what they've drawn on number 1. Okay, but on number 2, this time it says take a sample of any 2. So it doesn't matter which 2, they picked 60 and 70, right? And it says find the mean. So to find the mean, I would add 60 and 70 together and divide those by 2, and I get that the mean of those 2 scores was 65. Here's where I get my sampling distribution. I take all possible samples of size 2. So that'd be 60 and 70, 60 and 80, 60 and 90. So there's 6 different arrangements of 2 people that I could choose, right? And I could get the mean of all of those. So right here, what we've done is we've graphed the mean of all of those samples. This is what's called my sampling distribution of X bar, and X bar just means the sample mean. So each dot right here represents the mean of a different sample of size 2. Okay? And so then what I can do is look at the middle of my graph. The middle of the sampling distribution should show a mean that matches the mean of the entire population. Okay? And that should work every time, and that's one of the purposes of sampling distributions. Okay? So again, just to reiterate, when you take many samples, the mean of all those samples put together should match the mean of your population. All right. Now, you can also do this for things other than the average. You can do it for a proportion. So let's look at an example of that. So it says, to determine how much homework time students will get in class, Mrs. Lynn has a student select a simple random sample of 20, I'm assuming those are poker chips, not potato chips, from a large bag. The number of red chips in the simple random sample determines the number of minutes in class students get to work on homework. Mrs. Lynn claims that there are 200 chips in the bag and that 100 of them are red. When Jenna selected a random sample of 20 chips from the bag without looking, she got 7 red chips. Does this provide convincing evidence that less than half of the chips in the bag are red? So let's talk about what's happening here. So our population is 200 chips, at least according to Miss Lynn. That's what she tells us. And she tells us that the proportion of those chips that are red, and that's why you're seeing the little p here, is 100 out of 200, which is 50%. Let's compare that to what happened when the student took a sample. So her sample size was only 20 chips, and she found in her sample that only 7 of the 20, which is not half, were red. And so what we want to know is, does this one sample provide evidence that Mrs. Lynn is lying, right? And so what we're going to have to think about is, what are my options? Well, it's possible that this student just got 7 out of 20 purely by chance, right? We don't expect exactly half of the chips to be red every single time that a student pulls some out of the bag, right? But it is also possible that Miss Lynn lied and that there are less than 50% of red in the bag. So what can we do to kind of assess what's happening here? Well, at this point, we would use some technology to simulate a sampling distribution. And so what we did here was we used technology to simulate 500 different samples of size 20, right? And so you would input that into the computer, and it's going to spit you out a dot plot right here, okay? And so what we're looking at is if there were actually 100 red chips in that bag. So if Miss Lynn was telling the truth, what should happen over time when we choose samples of size 20? Well, you can see that the most common answer should still be a 50-50 split if she's telling the truth, right? But you can also see the sampling distribution via technology shows that sometimes we're not going to fall exactly on 0.5 or exactly on a whole number even, right? And so here's what we're looking at. Our sample that this student chose was 7 out of 20. Okay, so that would be 0.35, which is right here. So even though that's not right in the middle of the graph, it doesn't look like it's unusual to get a sample with 35% red chips if Miss Lynn is telling the truth, right? So based on that, we would say no, a sample proportion of 35% or less isn't unusual. This one sample that we got out of this bag doesn't prove that Miss Lynn was lying, right? Getting 7 out of 20 might not be exactly half, but that doesn't mean she lied. Maybe we just got an unfortunate sample, okay? And so what we're looking for when we look at sampling distributions, if something is unusual, it will happen less than 5% of the time. And so when I look at that, let's say that the sample that this student got had been let's say like 3 out of 20, which is 0.15. Well, when I look at that, where that falls on the graph, that's right here. Only one of the 500 random samples generated by this computer fell that low. If that had been the sample the student got, that would have been highly unusual because out of 500 times that this sample was drawn via technology, that only happened one time. Right? That would be unusual. That would be when we would start saying, okay, Miss Lynn might have fibbed to us. All right. So a couple different things to know about sampling distributions, okay? It says to describe the shape of a distribution of sample means, does the shape of the population distribution or sample size affect this answer? The answer is yes, okay? So here's the thing. The shape of the population doesn't affect the shape of your sampling distribution unless you have a small sample size, because small samples are prone to errors, okay? So if the population distribution is stated to be normal, okay, then we can assume that no matter what our sample size is, the sampling distribution will also have that normal or that bell-shaped curve when I graph it, okay? If that's not stated, then I have to have a sample size of at least 30 in order to assume that I'm going to get that bell-shaped curve. Okay? So question 2, is it true or false that the mean of the sampling distribution should approximately be equal to the population mean? We already talked about that. Yes, that is true. Okay? Number 3 talks about the central limit theorem. So what is that? So the central limit theorem says that as long as our sample size is greater than or equal to 30, we can assume that our sampling distribution of means is approximately normal or bell-shaped. And the reason, again, that that is true is because when you get small sample sizes, outliers have a bigger impact. So let's say you have a sample of size 30, and you get one person on your survey who feels very, very strongly about something, right? Their results are going to have more of an impact in a smaller group than they would if you were sampling a group of size 100, right? That one person's opinion kind of gets buried there. And so in small sample sizes, one person's opinion has the ability to skew your results, where in a larger sample size, it doesn't. You're going to get that bell-shaped curve. Okay? Number 4, why does it make sense that the standard deviation of an entire population would be larger than the standard deviation of a sampling distribution? So just to remind you of what standard deviation is a measure of how far spread out your data is, And typically, we see the standard deviation of a population be far more spread out than the standard deviation of a sampling distribution. Why is that? It's because the standard deviation of a population is calculating the distance of each individual from the overall mean, right? So the population looks at everyone individually. However, when we are plotting a sampling distribution, we're looking at the distance of a group from the mean. And we would expect a group of people to fall closer to the average than maybe one individual, because what if that individual is an outlier? Okay, so then if the standard deviations for population and sampling distributions aren't the same, how do you find the standard deviation of a sampling distribution for means? You take the standard deviation that is given to you for the population and you divide it by the square root of your sample size. And that's this formula that is shown right here. Okay, so that little baby sigma there, that's your population standard deviation, and n is the size of your sample. Okay, so let's look at a few examples. So number one, if I told you that the proportion of people in a population who was allergic to shellfish was 0.03, which is 3%, what would you assume about the mean of the sampling distribution of proportions? Well, here's the thing. When I take a sampling distribution, I expect the middle of that sampling distribution to fall in about the same place as the middle of my population. So I would expect the mean proportion of my sampling distribution to also be 0.03. Okay, what's the formula for standard deviation when I'm dealing with a sampling distribution of proportions? Here it is right here. Okay, so in this formula, P is your proportion, and let me rephrase that. P is your proportion of successes. 1 minus P is your proportion of failures. So in that last example where we were looking at drawing chips out of a bag to determine how much time students got to spend on homework, P would have been your proportion of red chips. 1 minus P would have been your proportion of whatever color of other chips were in that bag. Maybe it was blue, right? And then again, N is your sample size. So how is this formula similar for getting the standard deviation when I'm dealing with a mean and not a proportion? Well, both formulas require you to divide by the square root of n on the bottom, which means sample size always impacts the size of your standard deviation. The bigger the size of your sample, the smaller your standard deviation will be because you can get more accurate the bigger your sample is. Your data will not be as spread out. Okay, so there are two conditions that must be checked when you are dealing with the standard deviation, when you are dealing with a sampling distribution of proportions, in order to assume that your sampling distribution is normal. What are those? So essentially, our sample size must be big enough to give us data to see what's happening. So we must have an appropriate number of successes and failures, and the way that we check that when we're dealing with proportions is we need to use this formula right here. N times P times 1 minus P. So N is my sample size. P is the percentage of those in the sample size who gave me a success. 1 minus P is the percentage who were considered failures. And when I multiply those together, it must give me a number greater than or equal to 10. And again, it's just because we've got to make sure that we see enough people or items in both categories to really understand what's happening with this data. Sample size is important. The other thing is we must check independence, okay? And in order to check independence, we are going to use the formula on the left right here, because that is what your MyLab software expects you to use. And what it says is that my sample size has to be less than or equal to 5% of the population size. And I want you to think about why that is. Let's say that you are sampling people in Bowling Green. Even if you do a good job and you do a random sample of 1,000 people, right? If you make that sample size too big, you're eventually, because you're looking in the same town, going to start getting people who are friends with each other, or you're going to start getting people who are from the same family or from the same church. So you're going to start getting people whose relationships impact one another's opinions, and then your results are no longer independent. So we want our sample size to be big enough to see opinions on both sides of the issue, but we don't want it to be so big that we can't claim that our individual results were independent from one another. Okay? All right, so if you are asked to find the probability that something occurs, what button should you use in your calculator? We're going to use that normal CDF button that you saw in previous units. And as long as these two conditions right here are met, you can use the normal CDF button to answer any questions that you're given. Okay? So let's look at an example. So number 5, you are given the following information about a population. The percentage of people in favor of a new law being passed is normally distributed with a proportion. So I know that in just a minute when they ask me for the standard deviation, this is the formula that I'm using. I want to make sure I'm using the formula with the P in it, right back up here, because that's the information that I'm given. I'm dealing with proportions, so I want to use the standard deviation formula that uses proportions. Okay, so it tells me that it's normally distributed, so I know that this population is bell-shaped. It has a proportion of 0.35, and we're not told what we're being asked about here, so we don't know what that proportion of people agreed with. And it had a standard deviation of 0.081, okay? And let's talk about what you would type in your calculator to answer the following question. So let's say the question was, find the probability that in a sample of 100 people, 40 or more of them are in favor of the new law passing. So that means we're looking for a probability that X is greater than or equal to 0.40 or 40%. So 40% in favor, okay? So what we would do is we go to normal CDF. We would set our lower boundary as 0.40 because we're looking for anything greater than that. We would set our upper boundary as some huge number. You could do 1,000 or 10,000 because technically the normal curve goes to infinity. Our mean would be 0.35 because we assume that the mean of the sample is going to match the mean of our population. Okay, and we're given that information in the problem. But then our standard deviation for a sample is going to be different than it is for a population. And that's when I use that formula that I gave you on number 2. So to find the standard deviation, you're going to do the square root of 0.35. So that's the people in favor of the law. So that's your successes times 0.65. Those are the people that we're considering failures. They are not wanting to see this law passed, over our sample size, which in this case was 100, and that gives us 0.0477. So when you typed this whole thing in your calculator, you would hit normal CDF. All right? And then these are the 4 things that you would type in after that. Okay? All right, so let's look at an example where we're looking at the sampling distribution of the mean. So on A and B, your formulas are given for you there. So on A, it's just a reminder that the mean of a sample should match the mean of your population. On B, we have the formula for finding the standard deviation when we're dealing with the sample. Okay, so here's what we find out on example C. The average GPA of a high school senior in the U.S. is a 3.0 with a standard deviation of 0.45. Suppose you decide to see if this holds true in one county. So you consider taking samples of size 25 or size 50. Which one would be more appropriate in this case and why? So here's the thing. First of all, in general, a bigger sample is better than a smaller one because it gives us more information and it means that outliers won't have as big of an impact. But the other reason is that if we want to use the normal CDF button in just a minute in our calculator, we have to be able to assume that this data is normal. And we can't do that if our sample size isn't at least 30. Okay? So right here, 50 is going to be our best option. All right, number 2 says, if I were to graph my sampling distribution, what would it look like? Well, as long as we use sample size 50, we can assume that that shape is going to be normal or bell-shaped. Our center for a sample should be the same as the center for the population, which was 3.0. Our spread is what's going to be different. Okay, so when we do the spread of a sampling distribution, because we are looking at groups and not individuals, our standard deviation is going to shrink a little bit. So the formula for our standard deviation is going to be 0.45, which was the standard deviation of the population, over the square root of 50, and that gives us 0.0636. Okay, as our standard deviation for our sample. All right, so number 3 says, what is the probability that in your sample, the average GPA is less than 2.6? Okay, so this is where we would pull out our calculator. That's not something that I would ask you to do off the top of your head. So let me get that pulled up just quickly here. And we're going to go to normal CDF. And again, we're only able to do that because our sample size was bigger than 30. And looking at this information, so our lower boundary, we're not going to have one. So we're going to put a really big number in. Our upper boundary is going to be 2.6. So what we're doing by setting our upper and lower boundary that way is we're saying we're looking for anything that is less than 2.6. 2.6 is as high as it goes. What was the mean we were given? That was 3. And then our standard deviation was 0.0, where did that go? 0.0636. Okay, 0.0636. And we paste that. Okay, and how do I read this information? So this is scientific notation. This is saying that the answer is 1.6 and then roughly times 10 to the negative 10. So what that means is we would have to move our decimal place 10 places to the left. So it's like 0.00000016. That is a very tiny probability, right? So with that in mind, okay, this is taking just a minute to load again for some reason. There we go. It says, what's the probability that in your sample, the average GPA is going to be less than 2.6? It's really, really tiny. It's 1.6 times 10 to the negative 10. Would this be considered unusual? Absolutely. Why? Because that number is way less than 5%, which means it has a less than 5% chance of happening if we already know that our population has a mean of 3, right? So we're not expecting to get a sample of size 50 with an average that's way far away from the average of our population. That's unusual. Okay? What about 4? If you took multiple samples, what percentage of sample means would fall between 2.5 and 3.1? I'm not going to go type this one in the calculator, but if you did, the only thing that would change is your lower boundary would become 2.5, your upper would become 3.1, your mean and your standard deviation would stay exactly the same. Okay, and let's see here. There are a few more examples. I'm not going to go through those right now because for the most part, those are the same thing as what we've already seen. Okay, and all right, that is the end of Unit 8.